right, so we're going to get started on chapter 8, which is all about basic bonding things. So hopefully we're good with compounds, we're good with naming things, we're good with electrons. Now we're going to sort of put those concepts together and like how do these things, like why do they stick together in those specific formulas? So as far as chemical bonds are concerned, we're going to divide it up into 3 basic types of bonds. We've got ionic, covalent, and metallic. We're going to spend most of our time, we'll do a little bit of talk on ionic. We're going to spend most of our time right here in this covalent or sharing electron department. So with ionic, that means that we have something that has a positive charge and something that has a negative charge, and they're coming together. So this is our metal and nonmetals. And there's an electrostatic attraction between these ions. So they're sticking together like 2 ends of a magnet. Covalent materials, which for the most part are nonmetals or molecular compounds. Sometimes we'll see them called molecular compounds instead of covalent. This is where our electrons are shared. So in this instance, because it's 2 nonmetals, both of them are very greedy for electrons. They don't want to give the electrons up. Oh, Emma, I like your doggy in the background. They're greedy for electrons, so they have to learn to share the electrons. We're not going to transfer. And then metallic materials, these have situations where electrons are just sort of free to sort of kind of shift around the material. That's why we can conduct electricity through metals, because we have this nice flow of electrons. So I do want us to look at a Lewis dot structure. So this is a way to denote elements with their bonding electrons. And when I say bonding, or its potential bonding electrons. So when I'm talking about this, I mean that I'm looking at which electrons are actually going to be involved in like making a compound. So for instance, carbon is in column 4. So it has 4 valence electrons. So when I'm going to draw its Lewis dot structure, its Lewis symbol, I'm going to put the symbol for carbon, and then I'm going to fill in 1 electron, 2 electrons, 3 electrons, and then 4 electrons. I'll always fill them in singularly and then go back and double up. All right, there are 4 sides. Each side has will hold a maximum of 2 electrons. If for some reason you are in like column 8 here, you have 8 valence electrons, you've created what's known as an octet. And an octet is very stable. So everything, all of these compounds, or all of these elements rather, are going to try and gain and or lose electrons to get to this octet. All right. So if I want to do the electron configurations, for instance, or rather the Lewis dot structure for aluminum, I only look at the fact that it's in column 3, and I'll give it 3 electrons. 1, 2, 3. Now I know aluminum has 13 electrons, but I don't put all 13 in there. Why? Because the electrons that sit underneath these 3 are all internal electrons. They're not having any effect or any play on bonding. We only look at valence electrons. You can see that the Lewis symbol is going to be the same, or the Lewis dot structures are going to be the same for anything in the same column, right? So boron has 3 electrons around it. Aluminum also has 3 possible bonding electrons around it. Oxygen, sulfur, they are in column 6, so we would see 6 valence electrons for them. Doesn't matter what row you're in, we're talking about what column we're in. So the number of column that you're in equates to the number of valence electrons. So when looking at ionic bonding, this is where we have metals and nonmetals, minus group 8, which is the noble gases. So we have some sort of an electron transfer here, or an electron from the metal is going to move over to the nonmetal, and it may be 1 electron, it could be up to 3 electrons. This is a very exothermic process. So when we make this bond, we release a lot of energy. So here's an example. We have sodium, we mix it with chlorine gas. So we take the little sodium piece and we drop it into chlorine gas, and those will combine, transfer electrons, and come together to form NaCl. When that happens, we're gonna produce a lot of heat, all right, or the container is gonna get warm. So here is the Lewis dot structure for sodium. So sodium is in column 1, so we give it 1 electron to play around with. Chlorine is in column 7, so it will actually have 7 electrons around it. Now, when these two are in their uncharged state, so they have the same number of electrons as they do protons, neither of them are creating an octet, or neither of them have that 8 on the outside. So what will happen here is this little electron from sodium is going to transfer over to the chlorine. That electron will go away, and sodium now has a plus charge. Now there's no electrons that are written around it, but there are actually, in fact, 10 electrons. So if you look where sodium is, if we drop back 1 electron, we get to the configuration of neon. So this has a complete octet. This is, sorry about that, this is stable, right? We don't draw the octet in, we don't draw the 8 electrons from the lower onion shell, but it is in fact complete. It's a little clearer with the chlorine. When this electron transfers over, what happens to that set of 7 electrons? It now becomes 8 electrons. We've satisfied our octet rule. So by transferring this 1 electron, sodium has 8 in its outer shell, and chlorine also has 8 in its outer shell. So they've both satisfied their octet. Now, sodium has a plus charge and chlorine has a minus charge when it creates this octet. So what happens to a plus and a minus charge? They're going to stick together, and now you've got an ionic bond.
Will you repeat whether or not this is one of the stronger bonds?
As far as the an ionic bond?
Yes.
Yeah, it's a strong bond. It's a strong bond. So a couple things for ionic substances, they tend to be brittle because they create this 3-dimensional lattice shape. So it's not that, it's not like a molecule where you have 1 sodium and 1 chlorine and they're stuck together and they're a single unit. In this case, we've got them lined up in a 3-dimensional lattice structure. So this chlorine is actually sort of connected to a couple different, the sodium is connected to a couple different chlorines, the 4 on the side, the 1 on the bottom, and the 1 on the top. Same thing with the chlorines. They're connected to all of the sodiums that surround it. So it creates this sort of interwoven 3-dimensional lattice. Because of that, these structures tend to be brittle as opposed to like our non-metal stuff or our covalent stuff. They have high melting points because it takes a lot of energy to break this lattice structure with heat. They're also crystalline. And this here says cleave along smooth lines. Cleave means that they break. So these materials, if you were to take them and break them, they'll have these really kind of interesting repetitive breaking patterns. Like salt, for instance, will break in this sort of cubic shape. So as far as energetics of ionic bonding, here is an image of energy. Sorry about that. So we've got energy, so higher energy up here, lower energy down here. So anytime we are going from an ion or 2 ions in its gaseous form to the solid, this is known as the lattice energy, okay? The amount of energy it takes to change gaseous into a solid compound version. And lattice energy is dependent on a couple different things. So anytime we form one of these solids, there's a huge amount of energy released. So let's go back here. You can see to go from the individual gaseous ions of sodium and chlorine to the salt, the solid salt, we're going to release energy or have an exothermic situation. So whenever we're going from the solid and we happen to be going into its individual ions, we will actually absorb energy. So the formation of a solid releases a huge amount of energy, or it's exothermic. We're not going to get too much into these details, the step stools of breaking them up, but know this section here of lattice energy. So here is an example of a lattice energy. So we've got sodium chloride. We're going to break it up into its gaseous ions, and it will create an endothermic reaction, or its lattice energy will be plus 788 kilojoules in every 1 mole of salt. The reverse of this reaction is exothermic. So if I'm instead going from the Na plus gas, Cl minus gas, if I'm going from my gaseous into the solid, this is where it's exothermic. Okay, this will be minus 788 kilojoules per mole. So to produce a salt, it's exothermic. To break up a salt, it's endothermic or positive. And so when you were talking about this lattice energy, you can kind of think of it as the amount of energy it takes to release one, or to break up 1 mole of salt into its individual ions. Here's a couple different lattice energies. So LiF has a lattice energy in kilojoules per mole of 1030. LiCl is 834. Why are these different? It has something to do with the size of the materials. And then if we look over here, this has a larger charge. Mg has got a 2+ charge. That's a higher energy, and that corresponds to charge and size of the atoms will tell you how big your lattice energy is, or will let you know which one has a bigger lattice energy. So some of the properties, as you increase your charge, you are going to increase your lattice energy. So none of these really show that. So I'm going to write it down. I'll write an example down here. So for this first one, increasing charge on the ions will increase your lattice energy. So if I've got something like NaCl, this is a +1 charge, and this is a -1 charge. This is going to have a lower lattice energy than something like CaO. Ca has a 2+ charge, O has a 2- charge. So you can kind of think of these as like your strength of the magnet. This is a lower strength in its magnetic attraction versus the 2+ and the 2-. A stronger magnetic attraction is going to create a stronger sticking quality to the ionic bond, which is going to make it harder to break apart, or will increase the lattice energy. We could even throw another one in here and say something like a really big lattice energy would be like aluminum and, let's do aluminum and nitrogen. 3+ charge and 3- charge, right? That has a really strong magnet, 3 times as big as these. So this is going to be really, really hard to pull apart. So we expect to see lattice energy increase as our charge increases. The other thing is that that determines lattice energy, or you don't have to have the lattice energies memorized, but you do want to know how they relate to each other, is size. So lattice energy increases with decreasing size of the ion. So the smaller the ion, the larger the lattice energy. The smaller the ion, the larger the lattice energy. So I'm going to compare LiF with NaCl. Li and F are in row 2. Both of them are in row 2. Sodium and chlorine are in row 3. So these are bigger. These are smaller. The smaller guy is going to have a bigger lattice energy.
The last thing I heard you say was LiF was in row 2, and then you cut out.
Okay, LiF is in row 2. NaCl is in row 3. Can you hear me now, Brittany?
Yes, I can hear you.
Okay, cool. So these are smaller. These are larger atoms or larger ions. The smaller guys are stuck closer together, or they have a smaller atomic radius. So their protons and electrons interact with each other a little bit easier. They're closer together. They're going to have a stronger pull towards each other. So these guys are like they're like best buddies. Okay. They're sitting like right next to each other on the bus. These guys are friends, but they're like not close enough to be in the same seat. Let's say on the bus, they're sitting across from each other. So they're sort of friends, but they could break up a little bit easier. So the smaller the atom, the greater the lattice energy. Or you can think that as far as charge is concerned, it's directly related. As one goes up, the other goes up. With size, it's inversely related. As one goes up, the other one goes down. Don't worry about this equation. I'm not going to test you on that, okay? But do know these things. So if I was to give you something like, hey, NAF and NAI, which one is going to have a higher lattice energy? You're going to go with this one because F is smaller than I. So they have the opportunity to get closer together. All right, so electron configuration of ions. So main group metals will tend to lose electrons, which results in an electron configuration to the previous noble gas. So this is something that we've sort of already gone over from our electron configuration. Metals don't want electrons because if they gained electrons, they'd have to gain a lot of electrons to get to a noble gas. It's much easier for the metals on the left side of the periodic chart to strip away 1 or 2 or 3 electrons to get to that noble gas configuration. The opposite is true for nonmetals, just because of, partially where they sit on the periodic chart. So our nonmetals like nitrogen, oxygen, fluorine, chlorine, all those things on the right side, it's easy for them to grab a couple of electrons and become like a noble gas, right? Fluorine, it only needs to get 1 electron and it becomes neon. Chlorine, again, only needs 1 electron, it becomes argon. Note that the transition metals do not follow the octet rule, so they're not necessarily trying to get to the configuration of a noble gas. We're not going to really spend a whole lot of time on transition metals, okay? We're going to be spending more time on main group elements and then just non-metal stuff. So don't stress too much about transition. So in covalent bonding, and you can give yourself a note here, covalent bonding is happening between nonmetals. And what are nonmetals? Nonmetals tend to form anions, or they're greedy for electrons. They want electrons. And if you have 2 nonmetals, then you're going to have 2 things that want to eat up electrons. So what has to happen here is they've got to share their electrons. So atoms in this situation will be sharing electrons to get to an octet as opposed to transferring electrons. There are a couple things that play out in a covalent bond and how that bond is going to look. One of those is the attraction between electrons in the nuclei, repulsion between adjacent electrons, and we'll get into that. That sort of determines the shape, and then repulsion between nuclei. In order for these 2 things, so this atom here and this atom here, to come together, the attraction needs to be greater than the repulsion. So when looking at covalent bonding and why certain things bond in the way that they do, we want to create these things called Lewis structures. So we had the Lewis dot diagrams for each individual element. A Lewis structure shows us how electrons are actually being distributed within the molecule and are shared. So what we always want to do is we want to start by trying to give each atom the same number of electrons as the nearest noble gas. So everyone, we're going to try and satisfy an octet, except for hydrogen. Hydrogen and helium are going to be happy with something known as a duet. So they really only like to have 2 electrons. So we're never going to have hydrogen getting 8. Hydrogen will always have 2 electrons. So write that down somewhere. We'll use it so much, hopefully it becomes second nature. Sorry, I can hear my daughter screaming bloody murder out there. What's going on? So here are two examples of Lewis structures for two diatomic molecules. This is H2, and then this is Cl2. Hydrogen, David, hydrogen always wants to get 2 electrons, okay? It doesn't necessarily mean it has 2 electrons when it's on its own, but it will bond in order to get 2 electrons. So if I look at hydrogen on its own, its Lewis structure looks something like this. So hydrogen has 1 valence electron. This hydrogen over here also has 1 valence electron. So it's actually more stable for these two to share these electrons. So instead of, hanging out by themselves, what they're going to do is put these 2 electrons between the 2 of them. And this bar right here represents 2 electrons. Okay, so when you see that bar, I want you to equate it to 2 electrons. So it's more stable for the hydrogen to be bonded to itself, because now this hydrogen has access to 1, 2 electrons, and this hydrogen also has access to 1, 2. Chlorine, normally we give it 7 valence electrons because it's in column 7, right? So close to having 8 valence electrons. So what can happen is another chlorine that also has 7 valence electrons, they can decide to share these 2 electrons. Now they each have access to 8 valence electrons. This chlorine has access to 1, 2, 3, 4, 5, 6, 7, 8, because they share the ones in the middle, and this one also has access to 8. So whatever group number, we've already said this, but whatever group number that you're in is the number of valence electrons that that material is going to bring to the table. So when we're trying to make these structures, first thing you want to do is add up how many electrons do you have to even play around with. So each one will, for instance, hydrogen brings 1 valence electron to the table. In this picture here, fluorine brings 7 valence electrons. So I have a total of 8 valence electrons to mess around with. So I don't really like these, the way that they state these. This I feel like this is sort of unnecessary. So I'm going to skip over to the notes, guided notes. I think there's better explaining how to do these Lewis structures. Not there yet. Okay, and we'll come back to polarity. But for these Lewis dot structures, they're going to be a diagram that shows where the electrons are in a molecule. So it's a diagram that shows electrons in a molecule. And there's a couple different types of bonds. So a single bond, which is what we saw with hydrogen bonded to itself like this. A single bond is composed of 2 electrons, or it's got 1 bond, okay? That's important to note because sometimes questions will be asking you how many bonding electrons are there, or it'll be asking you how many bonds there are. So the number of bonding electrons is always twice the number of bonds because we assume every bond contains 2 electrons. A double bond then will take on 4 electrons, and it will be 2 bonds. So we see these different types of bonds a lot with carbon. So carbon bonded to itself, we can get a single bond, or carbon can be a double bond. A triple bond, you guessed it, is going to be 6 electrons. And it's going to be 3 bonds, hence the triple. We'll have 3 like this. There will be no quadruple bond or tetrabond. Okay, so the maximum number we can ever have as far as 2 adjacent things bonded to each other is going to be a triple bond. My single bonds are going to be the longest and the weakest. My triple bonds are going to be my shortest and strongest. Why? Well, think about if you had just like one branch, one relatively long branch, and you were to break it, it'd be relatively easy to break. But what happens if you have 3 shorter branches stacked up next to each other and you try and break those together as one unit? It's much more difficult. Some other things, so octet rule. So this really applies to everything. They want to, atoms want to gain, lose or share electrons to create an octet. There is an exception to the octet rule, and that's the duet rule. So hydrogen and helium, like 2 electrons. So clear that out. So as far as not here. The polarity of bonds. So when you have, let's say we're looking at that carbon-carbon bond, and this is true for single, double, or triple, they can be either a non-polar covalent bond or a polar covalent bond. Now, a non-polar covalent bonds means that the electrons are going to be shared equally. So when I have something like carbon bonded to carbon, carbon has a similar electronegativity. And electronegativity you can kind of think of as like the atom's desire for electron or greed for electrons. So it's sharing equally. A polar covalent bond is going to be like H bonded to F. In this case, fluorine is much greedier than hydrogen is for the electrons. So we will actually have sort of, because the electrons, these 2 shared electrons are going to sit a little closer to the fluorine, there's going to be a negative charge on the molecule over here, and there's going to be a positive charge over by the hydrogen. And this asymmetry in charge over the whole molecule is what makes it polar. Non-polar is going to be this sort of equal sharing. So here they have F2. So fluorine and fluorine share the electrons equally. H and F, the electrons are going to stay more on the F side than the H side because F is a little bit greedier for the electrons. And something like LiF, this is a metal and a non-metal. Lithium's electronegativity is so low that it doesn't really have any desire for the electrons. In this case, it just transfers the electrons all the way over to fluorine. And if you're wondering what these electronegativities are, here's a chart of the electronegativities. So it's an atom's ability to attract an electron. These are sort of arbitrary numbers that are based off of fluorine. Fluorine is 4, and then the numbers decrease from there. They don't have any sort of units. It's just telling you that fluorine is the highest electronegativity. And then over here in the lower left, cesium is the lowest electronegativity. So metals do have a positive electronegativity, but it's very, very weak. So our electronegativity, if you want to write that somewhere, and this doesn't include noble gases. Why doesn't it include noble gases over here? Because noble gases have a complete octet, or in helium's case, a duet. So they have no desire for electrons. So they're not even talked about here. But you want to know that the electrons in the upper right-hand corner, or rather the atoms in the upper right-hand corner where fluorine is, and then oxygen, chlorine, very high electronegativity, lots of desire for electrons. And the atoms in the lower left-hand corner, not very large desire for it. So as far as this polar covalent bond thing is concerned, when two atoms share electrons unequally, so one is pulling harder than the other, we get this polar covalent bond. You can sort of think of it as with two kids, if you have a 3-year-old and a 3-year-old both pulling on a toy, they're sort of equal strength. So they'll pull it in a balanced way. But if you have a 3-year-old and let's say in this case, we have a 3-year-old and a 10-year-old, the 10-year-old is going to pull on those electrons much harder than the 3-year-old can. So the toy will sit in this vicinity more. So again, we get this, what's known as, it's called a dipole moment, or it's this asymmetry in charge over the whole molecule. So we've got a negative charge over here and we've got a positive charge over here. And this polar quality makes the molecule polar itself. So what's the cutoff? Well, you can look at the difference in electronegativity to determine how strong your dipole moment is going to be. The greater the difference in electronegativity, the more polar the bond. So here we've got H and I. They have a difference in electronegativity of 0.4. They're both sort of wimpy. So you can think of H as being like a 3-year-old and I as being a 4-year-old. Okay, so the difference between them is not very great. So the dipole moment, or the shift in charge, is not going to be very dramatic. But as one of these partners gets stronger, right? The H is the 3-year-old all through and through, wimpy the whole way up. But these nonmetals, these on the right, are getting stronger as we move up in electronegativity. So this very top one, you could say this is a 3-year-old versus like a 12-year-old. The difference there in their electronegativity, which we can see is 1.9, it's huge. It's going to have a stronger dipole moment, or it's going to have this stronger asymmetry in charge. I'm not going to expect you guys to be able to memorize the electronegativities or anything like that, but do know that a difference in charge or a greater difference in electronegativity creates a bigger dipole moment. At a certain point, your difference in electronegativity becomes so great that like one of them is so strong or so greedy for the electrons that it'll just transfer the electron over. And that usually comes around, usually greater than 1.9, or I think around 2.4 difference. That's when you just have a metal and a non-metal. So these guys over here are so wimpy for the electrons, and these guys are so strong for the electrons. They say, whatever, fine, just take the electron and they'll transfer it over. So these dipoles, or these dipole moments, it's when we have two equal but opposite charges are separated by a distance. We have this dipole forming. So we have a negative charge over here and a positive charge over here, and they are equal and opposite, but they are separated by a certain distance. And what this does is give you a negative charge over here and a positive charge over here, making the whole molecule polar. And then it can start to kind of stick to itself. So water does this. Water has a positive and a negative side and a positive side to it because of this asymmetry in the share of electrons. And so the negative side of one molecule will kind of stick to the positive side of another, and vice versa. So is a compound ionic or covalent? The simplest approach is just to determine, is it a metal and a non-metal? Then you're going to say it's ionic because they're transferring electrons. Two nonmetals are going to be covalent because they're both greedy for electrons. They're going to share electrons. There are exceptions to this rule, obviously, but that's the general rule of thumb. So we want to write Lewis structures specifically for covalent molecules. You can make these Lewis structures for ionics as well, but you don't really need to. If you guys can flip-flop charges, so it's sort of like extra work. But for covalent molecules, or when we're sharing electrons, these Lewis structures are really, really useful. So how do we go ahead and write the correct shape and or structure for something like this, PCl3? So first off, I need to calculate how many electrons I get to kind of mess around with, because I want to draw this Lewis structure. I want to figure out what the distribution is of electrons on these. So phosphorus is in column 5. So this has 5 valence electrons. Okay. Chlorine is in column 7. So it has 7 valence electrons. But in this thing, I get 3 of them. So I need to multiply this by 3. That's where these numbers are coming from. So we end up having a total of 26 electrons. Now, once the electrons have been added up, I don't care where they came from. They're all sort of in play, so we can share them amongst the diagram. Now, important thing to note, phosphorus, it brings 5 electrons, but it wants 8 electrons. Chlorine brings 7 electrons, but it wants 8 electrons. So make a difference here in your mind on what is the atom bringing to the table and what do they want in the end. They usually all want to have 8 electrons. That's why they're sticking to each other. If you have an anion, you'll add 1 electron. If you have a cation, you'll subtract 1 electron, and I'll talk about that in a minute. But let's just look at this one here. So as far as writing a Lewis structure, I'm gonna go over here to separate page. So we've got PCl3. We said we have a total of 26 electrons to play around with. So the first thing I need to do is draw a skeletal structure of this thing. So for the Lewis structure, I'm going to put the P in the center, and I'm going to put the chlorines on the outside. Why am I doing it that way? Well, in nature, things like to form a sort of balanced structure. So it wouldn't be very balanced for me to put chlorine in the center and then have a phosphorus on one end and a, come on, pen. Wouldn't make a whole lot of sense to have a chlorine and then a phosphorus and then 2 chlorines sticking out of here. This doesn't create a very symmetrical shape. So instead we want to go with P in the center. The next step is going to be sticking them together with a bond. My tablet is not working. Here we go. Okay. So I make my skeletal structure and then I'm going to stick them together. Because if it's in fact a compound, like we have written here, I've got to glue them together. From there, I'm going to make the outer guys happy first by giving them electrons, and then I work to the inside. You don't want to do it in the opposite direction, okay? You don't want to fill the inner guys and then work to the outer guys. You always want to do outer to inner. So I have 26 electrons to play around with. How many do I have on the board so far? So far I have 1, 2, 3, 4, 5, 6. Okay, so I've got 20 more electrons to put somewhere. I'm going to start with this chlorine. Chlorine has 2 right now. How many does chlorine want to have? 8. They all want to make that octet. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. I'm going to add 6 over here to give it 8. And I'm going to add 6 over here to give it 8. So now all of my chlorines are happy. I have a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons on the board. How many electrons do I have? I've got 26. So I need to put 2 more electrons somewhere. I'm obviously not going to put it on any of the chlorines. I'm going to add those electrons to the central atom. Check and make sure everybody is happy. When I say happy, that everybody is getting an octet. So this chlorine is happy with 8, this is happy with 8, this is happy with 8. And then what's phosphorus doing? It has access to 2, 4, 6, and 8. So there are 26 electrons on the board and everyone has 8 electrons. So what we've done is we've gone from a situation where, you know, this brought 5 and these brought 7 to now everybody has access to 8 electrons. This can also be drawn, sometimes instead of dots around the side, you'll see it like this. So P bonded to chlorines. And they'll put bars around each bar representing, sorry, that is supposed to be a chlorine. Each bar representing 2 electrons. Okay. I tend to do it like this, where my non-bonded electrons are a dot and then my bonded electrons are a bar. So let's do another one of these. And that's always going to be the way that you make a Lewis structure. You're always going to add up how many valence electrons you have to play around with, draw a skeletal structure, fill the outer guys, then fill the inner guy. And then if you can't satisfy filling the inner guy with the number of electrons, you'll make a double or triple bond, and I'll show you that in a minute. Let's do the Lewis structure for water. So H2O. Hydrogen is in column 1, so it brings 1 valence electron, and there are 2 of them, okay? Oxygen is in column 6, so it brings 6 valence electrons. So I have a total of 8 electrons to play around with. I can't have more than 8 on the board. I can't have less than 8 on the board. Now, when drawing a structure, I'm going to put oxygen in the center. Usually oxygen likes to be in the center. A lot of times the more electronegative thing likes to be in the center. It doesn't always happen that way, but hydrogen is always going to be what's called a terminal atom. It's going to be on the edges. Why? Because it only wants to have 2 electrons. So if hydrogen was in the center, it's going to get packed with more than 2 electrons. It doesn't like that. And also this is symmetrical, right? So if I did something like this, H, H, O, that doesn't look very balanced. All right, so after we've totaled up our electrons, and we've drawn our skeletal structure, we got to stick it together. So I'm going to bond these things to each other. There are 4 electrons currently on the board. I'm going to make the outer guys happy first and then work towards the central one. So hydrogen, actually in both of these cases, hydrogen is happy, right? Because hydrogen only wants 2 electrons. It wants a duet. Remember, hydrogen wants the duet. So I've got to find a place for these other electrons. Well, oxygen is not happy yet. So I'm going to put 2 electrons here, and then I can put 2 electrons here. So what I've created now is a Lewis structure where there are 8 electrons on the board, check. Each of my hydrogen has access to 2 electrons, and my oxygen has access to 8 electrons. So everyone has satisfied their octet and or duet. Any questions on those 2 so far? And how we're doing these Lewis dot structures, or where I'm getting those valence numbers from?
I have a question about the dipoles.
Yeah, what's that?
So why would they bond if they're not going to keep the electrons anyway? The weaker one.
They are keeping the electrons, they're just not holding on to them as strongly.
Okay.
So if I have something like H and F here, okay, and they're sharing these two electrons, they're not sitting in the middle like this. They're sort of sitting, they're like a little bit closer to the fluorine, or sometimes we'll draw it like this because you know these electrons are a probability cloud. So the electrons are probably going to be around the fluorine more often than they are the hydrogen. They still are holding on to them, but the fluorine is just greedier with it. You could almost think of the fluorine as taking like, you know, instead of taking just sharing the electrons equally, it's getting like 2/3 of the electrons, and hydrogen's only getting 1/3 of the electrons.
Okay.
They're sharing the cake, but fluorine's getting a bigger slice.
Bad friend.
Yeah, bad friend. Other questions so far? We're going to do more of these Lewis dot structures. Okay, let's do HCN. Come on, pen. What's happening here? Okay. So HCN, if we are going to do a Lewis dot structure for this, the first thing that we want to do is we want to add up how many electrons we get to play around with. So in this one, I get to have, one from the hydrogen, 4 from the carbon, 5 from the nitrogen, for a total of 10 electrons. Carbon in general likes to be in the center, so I'm going to put carbon in the center. Rule of thumb, if you have carbon, it's probably going to be in the center. So carbon goes in the center. I'm going to put nitrogen on one side and hydrogen on the other side. We've got our total electrons. I have to stick them together because it's a molecule, so I know that they're glued together somehow. Okay, bond, bond. Then I'm going to make the outer guys happy. Hydrogen is already happy here, so I don't need to add anything to him. Nitrogen only has 2 electrons, so I'm going to give him 1, 2, 3, 4, 5, 6. Then he has the 7 and the 8, and 9 and 10. So all 10 electrons are currently on the board. Hydrogen is happy, nitrogen is happy. What about carbon in the center? Carbon is not happy. So you cannot just add more electrons. Okay, I can't just go, well, there. Why? Because I can only have 10 electrons. So instead, this is where you start to develop a double or a triple bond. All right, so if you want to put in your notes somewhere, double and triple happen when there are not enough electrons to satisfy central atom. All right, never put double or triple bonds on until every electron is on the board. If you start putting double, triple bonds on and you haven't put all your electrons on, you're going to start to double up on things and it's going to get weird. So in this instance, we've got all of our electrons on the board and we're seeing that our carbon is not happy. So nitrogen has to go ahead and share. And I will show you that in a second. Come on. It's just one of those days, isn't it? All right, so hydrogen doesn't have anything to share, right? It's already sharing its 2 electrons. So what I'm going to do is take these 2 electrons and I'm going to move them here, creating a double bond. So let's erase these and let's put them right here. So carbon is getting closer to being happy, right? 2, 4, 6. It's still not quite there though. So what needs to happen is nitrogen again has to share. All right, so these electrons are going to get moved over. And again, you only want to do this once all the electrons are on the board. If you erase a pair, you have to draw them in somewhere else. If you're drawing them in somewhere else, you need to make sure you erase a pair. So you may want to count up after you've moved electrons around just to continue this idea of having just 10 electrons on the board. So here I've got 2, 4, 6, 8, and 10 electrons. Okay, I haven't added or subtracted. I've just sort of rearranged. Hydrogen is happy, nitrogen is happy, and now carbon has access to 2, 4, 6, and 8. He's also happy. So everybody is happy with 2 or 8 electrons. They're all balanced. I'm going to give you one to do. I want you to do methane. This one isn't too bad. CH4. Okay, so do the Lewis dot structure for that thing. Okay, so for this one, carbon brings 4 electrons. Hydrogen brings 1, and there's 4 of them. So we have a total of 8 electrons to mess around with. Carbon's going to go in the center. Hydrogen's going to go on the sides. And we're going to stick them together. All right, there's all 8 electrons. Hydrogens are happy, and actually carbon is happy. So that one's pretty simple to do. I want to do one with a charge. So if you happen to have something that is charged, like a polyatomic ion, BrO3 with a minus charge. The only thing that's going to be different about this is when you're calculating your valence electrons. So bromine is in column 7, so it has 7 valence electrons. Oxygen is in column 6, so it'll have 6 valence electrons, and there's 3 of them. Now we've got this negative charge. So what does a negative charge mean? It means that we've added 1 electron. So I have to add 1 electron here. If you were to skip that and you were to just add these, you would end up getting 25 electrons. You're always going to have an even number of electrons. Okay, sometimes you can have odd numbers. Yes, there are exceptions, but for what you guys will be tested on, you should always end up with even number of electrons. If you're not, you did something wrong. So here we should actually have 26 electrons to mess around with. I'm going to put the bromine in the center and then my oxygens on the side because it makes that nice balanced structure. Stick them together. Make the outer guys happy first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. 26 electrons. Oxygen's happy. Bromine 2, 4, 6, 8 is also happy. Now the last thing you want to do if it happens to be a polyatomic ion is just put it into brackets and put the charge around the outside of it. So everything we've talked about so far has been following the octet and the duet rule. Are there exceptions to the octet and the duet rule? Yes, there's always exceptions to the octet and the duet rule. There's exceptions to everything in chemistry. This is no exception. So ions or molecules with an odd number of electrons do happen. Sometimes nitrogen is okay with odd numbers, but I'm not going to test you on this. All right. So if you end up with an odd number of an electron, you've added it up incorrectly. Now this you will need to know that there are certain atoms that are happier with less than 8. Specifically, boron, aluminum, and gallium like to form 3 bonds or 6 electrons. Okay. So if we look at BF3, boron is bringing 3 electrons. Right. Fluorine is bringing 7 times 3. This is a total of 24 electrons to mess around with. So I'm going to put boron in the center. Fluorines are on the sides. Stick them together. Then we're going to add electrons until everybody's happy. So there are 24 electrons. All the fluorines have access to 8. This is good. The boron at this point only has access to 6. Now, one of you could be thinking, well, can't we take one of these and move it over so that boron then has access to 8 electrons? You could, but boron is actually happy with just the 6. So we're going to leave it like that. So do make a note somewhere that boron, aluminum, and gallium all like to have 3 electrons. Now, if there are ions that like to have less than 8 electrons, there are also atoms that like to have more than 8 electrons. These are known as expanded octets. A lot of times, these are bigger atoms, and they usually fall where, so we've got phosphorus, sulfur, and chlorine. It's going to be that, those atoms or bigger. Okay, so we're not going to see this for nitrogen, oxygen, or fluorine, the ones that sit above it. Maybe these guys are lower. So third row or underneath that. So an example here would be phosphorus with 3 chlorines. And I'm going to do this on a different page. And I think it was phosphorus with 5 chlorines, not 3. All right, PCl5. So I can already tell that this is going to be an expanded octet even before I've done it, because there are 5 chlorines that are going to be surrounding that phosphorus. So what we got to do here is add up all of our electrons. Phosphorus brings 5 electrons, chlorine brings 7 times 5 electrons for 35. So the total number of electrons we get to play around with here is 40 electrons. So I'm going to put the phosphorus in the center. I'm going to put the chlorines on the sides, and there are actually going to be 5 of them. I'm going to stick them together. And then I'm going to start filling in the outer guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 32, 34, 36, 38, 40 electrons. 40 electrons on the board. How many electrons does phosphorus currently have access to? It has 10 valence electrons here. It's 10 electrons. It's okay with that. So I think we'll stop there for now. We'll get into formal charge next time, which can have a little bit of an effect on whether we want to expand the octet or not. If you have any questions on this, ask me. We've got like 10 minutes. Otherwise, you are free to go. If you haven't voted yet, go vote. Otherwise, have a good rest of your day. Stop sharing.
Hey, when do you think you're gonna post the lecture video from last Thursday? I had to work, so I didn't get to see it.
Oh, is it not up?
No, I haven't seen it.
Oh no. I will do that like right now.
Awesome, thank you.
Okay,
Yeah,
it takes a couple minutes for them to process it to make sure that it's not inappropriate or whatever. So, but I'll do that right